Hello, we are happy to introduce our submission. Rapid Adaptation Robot. Accelerating Agent Adaptation via Discriminative Internal Model. Bipedal robot locomotion is a challenging problem that requires reinforcement learning (RL) methods to train effective policies. However, a common limitation of RL is the difficulty of transferring policies to different dynamics environments, due to the mismatch between the source and the target domain. To address this issue, we introduce Discriminative Internal Model (DIM), a novel approach that combines model-free RL with an internal model that learns to discriminate between different dynamics. DIM enables fast and robust adaptation of the agent to new tasks. This figure illustrates the framework of our proposed method, which consists of two phases, training and adaptation. In the training phase, we learn an internal model that captures the dynamics of the environment, as represented by the yellow trapezoid on the left. In the adaptation phase, we use the internal model to augment the state with virtual trajectories, which are then combined with real interaction data to train the policy. To avoid negative effects of poor augmentation data on policy learning, we also introduce a discriminative data generation scheme. To learn policies that can handle various robot dynamics, we use dynamic randomization as the first step. The dynamics parameters that we vary are COM, friction coefficient, damping coefficient, and distance of two legs. In addition, we train and adapt the policies on different walking velocities to test the task transferability. The internal model is a learned function that approximates the dynamics of the environment. It takes as input the state, action and a latent vector at time step t and outputs the next state, reward and a done flag. The internal model is trained end-to-end with a neural network by minimizing the loss function defined above. To train our reinforcement learning (RL) model, we adopt the Proximal Policy Optimization (PPO) framework, which is a state-of-the-art algorithm for continuous control tasks. We observe that the policy reaches a stable performance after 800,000 environment steps in the training phase. We design a bipedal robot simulator with Pi-Bullet and create various tasks to test how different methods can adapt to different scenarios. Our method is compared with other methods on tasks that involve COM, friction, and velocity. The comparison shows that our method outperforms the other methods in terms of adaptation performance. To speed up policy adaptation for new tasks, we use the internal model to generate a series of transitions that are similar to the new tasks domain. The internal model predicts the next state, the reward, and the done flag for the current state. We design a state discriminator that computes the prediction error as a measure of reliability for each state. The intuition is that a lower prediction error indicates that the internal model is more confident about the state. We evaluated the internal model's performance by visualizing the predicted future trajectory, as shown in Fig. We converted the predicted transitions to robot poses and displayed them in the first row of the figure. The shadow indicates the predicted robot pose and the solid indicates the actual pose. The curves indicate the joint trajectories. The results show that the internal model's prediction is accurate for the first 10 steps. However, the prediction error increases as the augmentation depth increases. We conducted another experiment to test the generalization ability of the DIM model. We created a robot and gazebo simulation, which uses a different physics engine from Pi-Bullet, and examined how well the policy trained with our method can adapt to a new simulator. The results demonstrate that the proposed method enables fast and effective transfer across different simulators. We evaluate the DIM policy on different friction and damping scenarios in the real world, such as smooth ground, rough ground, uneven ground and wooden floor. We pre-train the policy and the robot dynamics model in the gazebo simulator, and use a few real-world samples to fine-tune the policy. Since the real robot lacks some sensors, such as force sensors, we cannot compute the reward for the robot. Hence, we only use the reward predicted by the internal model to optimize the policy in the fine-tuning phase. The transferred policy enables the robot to walk on various friction and damping surfaces. As shown in this video, the robot walks stably on low friction ground. On high friction surfaces, such as uneven ground, the robot walks less stably, and the uneven ground causes large fluctuations in the robot's orientation. Comparing the results for different damping scenarios, as shown in the first and last video, the robot walks similarly on tiled floor and wooden floor. The DIM policy can achieve stable walking on both surfaces. However, the performance of the transferred policy is still worse than in the simulator. For instance, the real robot's gait is shaky, and its leg lift height and step length are quite different from the simulator. This could be due to various factors, such as reward estimation errors, motor control errors, environmental noise, etc.